So let's pick up again with computer systems. Last time we talked about why computer systems matter. We talked about George Boole and Boolean algebra, and we ran through sum of products and product of sums as two different ways to systematically represent a particular logical behavior with a Boolean algebra equation. And we want to talk today about simplifying those equations into something that's a little more compact and a little less expensive to implement. So remember that sum of products and product of sums do not automatically guarantee that they're at a minimum complexity. So the case we had before was a two-button door lock, and so we pushed B1 and we pushed B2. And we had either lock or unlock, lock being 0 and unlock being 1. And so we did this in two ways. We did a sum of products, which gave us this answer. We did a product of sums, which gave us this one. These are equivalent representations that give exactly the same behavior, but they are, one is more complex than the other. And so one is easier to implement than the other. So the question is, can we reduce the complexity of one of these or the other in a systematic fashion? And maybe not in this case, but in general, can we take our sum of products or our product of sums and reduce the complexity in a systematic fashion? And the answer is, of course we can. One way to do this is with graphical minimization. So graphical minimization is based on the application of this simplification that we're going to say that x and y, or x and not y, if we pull out the y's there, is going to be x and quantity y or not y. Well, y or not y is going to be just a 1, so the result there is just x. And so anytime we see this combination that we've got a y and a not y in this form, then we're going to say, well, that's something we can eliminate. That'll be something that we can simplify out. And so if we put this into our mapping, then you'll see that that's going to be represented by adjacent cells. Let's look at an example. If we've got our door lock, again, it's got two buttons, B1 and B2, and we've got this particular truth table, which is a little different from before. Now we've got two unlock conditions. But notice right away in the truth table that you've got B2s here being the only thing that's affecting whether the lock unlocks or not. And you can see right from the truth table that what we expect to see is that B2, the lock L equals B2, because B1 can be any value and it doesn't matter. B2 being true is what causes it to unlock. But how can we represent that in a systematic fashion? Well, let's fill in our mapping. So we'll put in our 0, 0, 1, 1. And we're going to collect the adjacent ones. And so you see we've got two ones that are side by side, so let's grab those two. And when we write out our our sum of products, here we are, we've got a not B1 and we've got a B1, and B2 is constant. Well, if we pull out that B2, so now we've got not B1 or B1 and B2. Well, not B1 or B1 is just 1, so the result is B2. So by being adjacent, that corresponded to a case that we can simplify, and we can throw out the value that's changing, the B1 in this case. The B2 is constant. So we can do that in a general sense. We can also do that with more variables. What happens in this case, though, if we've got slightly different answers, or we've got the ones are not adjacent, they're diagonal in this case, well, they're not side by side, we can write out our sum of products, but notice that there's nothing adjacent. If we apply our simplification, it just doesn't work. This map is what we call non-reducible. This is as good as it gets for this particular case. Our mapping does not guarantee an absolute minimum, but when we do this method, it will give us the minimum for the product of sums or the sum of products form, whichever one we're using. So there may be some, you may be able to look at it and design something that's slightly better, but using our systematic rules, product of sums, sum of products, if we use our systematic rules and we follow through the graphical minimization, that will be a minimum complexity for that method. But what do we do if we've got more than two variables? So in this case, we had B1 and B2, but if we want to add a third variable, say a B3, To represent it, we have to go in or out of the page. And when we go in or out of the page, we got a three-dimensional mapping. That becomes a lot more difficult to visualize and be able to do anything with. So what we'd really like to do is take that 3D mapping and map it down to 2D, but also preserve the adjacency. We still want the whole rule to work. So how do we go about doing that? Well, we need a different way to count. Right now we're counting with binary, 0 and 1, but we'd like to be able to count in a non-binary way, and that will enable this translation. How are we going to do it? Well, we'll do it with what we call gray code. So gray code is also a counting sequence. It looks like binary, but it's not quite binary. So in this table, you can see we've got decimal representation, we've got binary representation, we got a gray code representation. Now the gray code representation looks like binary. It's still zeros and ones. It's still going to be the same number of bits as binary, but the order is a little different. And it's still going to be unique representations here that 0 lines up with 0 in decimal, lines up with 0, 0, 0 in gray code. There is a distinct order, it just no longer matches our straight binary. So don't be confused, it's not actually binary, it's gray code. What's fantastic about gray code? Well, it's going to fix this problem, and it's going to fix another problem that you may not have thought about yet, and will be interesting come our discussion about actual implementation of these things. You see, when we've got multiple things going on, and we want to, in a system that we've implemented in a either in a computer or in analog ICs, in any case, there's this problem that if we want to read the data, and things are changing, then if we use straight binary counting and we're changing, it's possible to read the wrong intermediate value. So for instance, if we're counting and we're going from 0 to 1 to 2 to 3 in decimal, so that'll be 0, 0, 0, 1, 1, 0, 1, 1, there's this time in the middle where we might accidentally read the wrong value. And so the way this happens is that we've got propagation errors, or propagation delays, in our physical chips, in our ICs, in our computers, whatever we're implementing on. And so when we've got both of the bits, the 0 and the 1 and the 0, when they're changing simultaneously, they don't really change simultaneously. One of them has to change first and then the other, because there's non-perfect propagation delays between them, and certainly depending on how things are set up, it may be intentional that way. So there's going to be a time delay in there, a little tiny delay, and we're talking on nanoseconds, but it still is there, and it's still a possibility you're going to hit it when you've got the wrong value. So let's look at the cases here. When we go 0, 0, 0, 1, 1, 0, 1, 1, it's possible that the second digit, the 0, 1 to 0, 0, is going to happen first. Or it's possible the 0, 1 will go to 1, 1 first. But we don't know which one it's going to be, and either one is not really right. What we really want is that 1, 0 to end up. So if we fix this, we want to use a different counting sequence so that instead of one of those, we step through a slightly different sequence like this, where it goes 0, 0, 0, 1, 1, 1, 1, 0, and now you can see only one bit changes at a time. And so if we are worried about reading the data and reading a temporary incorrect value, which can happen, especially with real systems, then something like gray code, which only changes one bit at a time, fixes the problem. So let's step back here real quick and look at, again, our table of gray code values for the first 8 numbers. And if you go through these, you'll see that each time only one bit changes from one value to the next. So as it's counting up, there's never a possibility of a bad read. So let's look at 3 to 4. You can see only the one bit, the first bit, changes. If we, I suppose you could say it's the third bit, depending on how you're counting things. First bit from the left. If we look at straight binary, all 3 bits are changing, and so we've got all sorts of potential for bad reads. So that's why we use gray code in computers a lot of times, is because we're worried about that sort of circumstance. And it'll also help in our mappings, because it'll fix the same sort of problem. So how do we make gray code? Well, you can start with 1 bit and then go to 2 bits. This is the first way to do it. So if we start with 1 bit and we allow it to change 0 to 1, and we can write out the same thing and then reverse that sequence. So we'll go 0, 0, 0, 1. So then we'll reverse that sequence and we'll go 1, 0, and then we'll stick in a 1 on each of those. That is terribly written. Let's try that again. 1, 0. We could do the same sort of thing. So we'll write out the 2-bit sequence, prepend with a 0, reverse it, and prepend with a 1 instead. And so there's a general procedure for you. We're just going to keep reflecting it and prepending. We can also view it this way, that we're going to apply rule 2 here. They're all getting at the same thing. Here's our reflect and prefix method, same sort of thing that we can do. 0, 1, we'll reflect it down, and then we'll prepend. We'll take that, we'll reflect it down, and we'll prepend. It's all great code. It's just different ways to write out the same rule. If we use gray code, or if we don't use gray code, we may require a synchronizer or a handshake. So this is another option if we don't use gray code. A synchronizer would be a clock signal, so the clock signal is going up and down, up and down. It's a square wave. And so then everything would be clocked to start at either a rising or a falling edge of the clock signal, and so everything is always happening at the same time. And so if we wait just a little bit after the start of the clock signal, then we always know that everything is fixed. We could also handshake things where everybody has to communicate that yes, we're ready to go before we actually transmit data. If we use gray code instead, then there's no need for a synchronizer because there's never a bad read. Everything is always exactly what it's supposed to be. There's no intermediate values. And so anytime that we want to read, we can. So we can go with asynchronous communication. It's fine. So that's a great thing about gray code, is we can take out the need for a synchronizer. So if we take our gray code and we go back to our graphical minimization, now that we're at least familiar with gray code, we can extend this to 3 to 6 variables, and we call this a Carnot map. But notice in this case we got B1 and B2 on the top and B3, B4 on the left, and we're counting from 0 on up in gray code. So on the top row there we go 0, 0, 0, 1, 1, 1, 1, 0. That's gray code, and it's 2 bits, B1 and B2. And we do the same thing on the left, 0, 0, 0, 1, 1, 1, 1, 0, and it's 2 bits, B3 and B4. And with this, we have taken 4 variables and put it into a 2D, and we preserved adjacency. So we can still count that yellow boxed 1, 1 as adjacent, and we can still wrap this around and count that 1, 1 in red as adjacent, so they're wrapped around top to bottom. So this still has our adjacency, it still works for our minimization, and it allows us more variables, which is great. Only up to 6 though. So if we've got our 3-button door lock, same rule for minimization, but in this case we've got 3 buttons, B1, B2, B3, and we've got a couple different combinations that are going to work for unlocking it. So we can take that truth table and we can put it into our mapping, and notice that we've got 5 different 1s in that mapping. And so if we write out our sum of product, we've got not B1 and B2 and not B3, or B1 and B2 and not B3, or B1 and B2 and B3, or B1 and not B2 and B3, or not B1 and not B2 and B3. There's our 5 different combinations. And you can see that this is pretty complex in terms of number of terms. So we'd like to be able to reduce it. And right away, if you're looking at it, you can see that there's some different things that are adjacent. And there's different ways that you can write out the adjacency. So let's do the adjacency. We can say, well, those 2 are adjacent. And so that's got our B1 that is, let's see, the B1 is changing. The B2 and the not B3 are not changing, so we'll just throw out the B1. We can say in green that these 2 are adjacent, and the B2 is changing, so the B1 and B3 is not changing. And we can go around the outside there in the red, and that'll be that B1 is changing, and so not B2 and B3 is not changing. And there you go. We have reduced this in complexity by quite a bit. We've gone from a lot of different terms there. Well, it's still it's gone from 5 terms to 3 terms, and then the 3 terms are also more simplistic in that they've only got 2 inside them. So it's a lot less terms. So that's our multi-input Carnot map, or K-map. We can also eliminate multiple pairs together. So if we had all 4 of the ones in a square like this, well, we just grab all of them all together, and we can say, well, B1 and B3 are changing, so the only thing left is B2. So we can make bigger groupings of pairs, and that makes things a lot simpler when we make bigger groupings of pairs. Notice it has to be a square in this case, it's not an L shape. And we can extend it to 4 variables. So in this case, we'd have a square there, so that's our B2 and not B3. We could have a square there, that's going to be our B1 and not B4. We can grab this one, and notice that one in the middle there, here, has been put in 2 different boxes, but that's perfectly fine. So we'll have not B1 and not B3 and B4. And there we go. So we can do this up to 6 variables using multiple tables, but beyond that we have to use other techniques. So this works really well up to 6 variables. It's a nice visual way to do it, but it is all application of the same simplification rule. What about if we have an input that is impossible to reach? If we have something that's impossible, we might call it a don't care and label it with an X, as in the upper left block. Now, if we do that, you can see that in this case, if it's a don't care, we can call it a 0 or a 1. We might call it, well, let's just see which way I did it here. So we got a group of 4, we got a group of 2, we got a group of 2. So that's our one way to do it, if we assume that the X is a 0. Or we could assume that the X is a 1, and we could grab that whole thing in there, which would reduce the need for the green grouping and makes it a little simpler. So we can use it whichever way makes sense, whichever way is convenient for our minimization. Why would we do this? Well, we can do this for error checking, we can do this for circuit minimization, but the big thing that I've run into is there are certainly input cases that just shouldn't happen. So let me give you an example of one of those. This is an example that we used a couple years ago. We had a thermal sensor, a front sensor, and a rear sensor on a robot, and it was locating objects and then trying to differentiate them based on temperature. And so what you can see right away is that ignoring what the sensors are doing, there are cases where the motor drive is off. And if the motor is off, then why would I care about the direction that I have told the motor to go? Because the direction is irrelevant, I'm not moving anywhere. So those are don't cares. They can be whichever value, it's not going to make a difference. So if I put that into a truth table, the don't cares become X's. I've changed the on-off and directions, because the directions I could figure out how to do those. They're all going to be 1s and 0s, and so I can come up with 2 mappings, one for the drive motor and one for the drive direction. And if I group my adjacent ones, you can see that I've come up with simplified representations of the drive motor and the drive direction. The drive direction, for instance, is just not FS. You can see that in that case, not FS is going to correspond to, let's see, so here's a 0, so we get a 1. Here's some 0s, so we'd get 1s. Oops. Here's some 1s, so we get 0s, and here's some 1s, so we get 0s. So it doesn't, boy, that's a touchy screen. So you'll notice that in this case, we get some of the X's turn into 0s, some turn into 1s, but it doesn't matter because the motor's turned off. So that's an example of a don't care. We don't care what the actual output is going to be, it's just going to be whatever is simple. Another sort of special case you're going to run into is called a hazard or glitch. And this is a short signal that's generated when inputs are changing, and it's spurious. We don't want it. So for instance, in this case, we've got, there's our adjacency, and we can draw this out. We're going to talk about pseudocode in the next one, but here's an example of pseudocode. These are inverters here. we're going to OR things together, and we're going to AND things together. Excuse me. So we've got our different groupings here, and we've got our 3 different paths for the sum of products. And so let's look at what happens when B3 changes. When B3 changes, it's going to go through the invert, it's going to go through the AND gate, and it's eventually going to end up in the OR gate. But when B3 changes, B2 and not B3 is also going to change, but there's going to be some time delay because it takes a little bit, when B3 changes, it takes a little bit of time to get through the inverter, and then it's going to take a little bit of time to get through the AND gate, and so there's a little bit of a time delay before the B2 and not B3 shows up at the output. Well, so what happens to the B1 and B3 and B4? Well, that's going to have a slightly different propagation delay because there's not an inverter and there's an AND gate, but it may not be exactly the same as the AND gate in the B2 and not B3 case. And so there's going to be a different time delay associated with it. You can see there's a little bit of a gap between when the purple signal goes down and the green signal goes down. And so the lock is going to look at this and it's going to say, well, I'm going to OR those together. So there's going to be this momentary time when it's going to go low because B1 and B3 and B4 has gone low and B2 and not B3 has gone low. And again, it's shifted a little bit to the right because of propagation delays. But there's going to be this little time where it drops low. And what we look at and we say, well, that should never have happened. If we look at just the algebra, that shouldn't happen. But it does happen because of the propagation delays associated with our individual components. There's a delay between when they see an input and when the output is generated. So what we want to do is we want to look at how does this affect our system. If we're just dealing with a static mapping, which is to say that the output depends only on the current value of the input, then an input glitch shows up as an output glitch. And so if we're running this through, say, a motor, like a low-pass filter, it's going to filter it out and it doesn't usually cause a problem. And it may cause a momentary problem even if you're not connecting it to a low-pass filter because it's very short. The issue comes in is if the device is dynamic using sequential logic, which is going to be our next big topic, then there's a memory effect, and so that glitch gets stored in memory, and other things that depend on it are going to continue to happen, and so we might have all sorts of stuff happen. If we've got a counter, so for instance we're counting the number of times that this has happened, our count's off. So how do we go about getting rid of glitches because they're bad and they're going to screw up all of the subsequent behavior of a sequential logic circuit? Well, one thing to do is we de-minimize the circuit. We say, okay, I've minimized the circuit, but maybe I went too far, so let's back it up a little bit. So instead of doing all of the adjacent things, let's go back and do some of the adjacent things. There's some term that doesn't change, so that when this B3 changes, there's one term in there that holds the line and keeps it constant. So let's go back to our original case. We've got these adjacent values, which gives us this, but there's also this red one. And see, this red one is not going to depend on B3. So if B3 changes, the red one continues to maintain the output. And so it makes our circuit a little more complicated. You notice we've got an extra AND gate in there. But what will happen is because we have that extra AND gate and the extra AND gate does not depend on B3, then when B3 changes and B2 and not B3 changes and B1 and B3 and B4 changes, the extra one, the B1 and B2 and B4, does not change. Whoops. And so the lock is constant all the way across. It doesn't have a glitch anymore. And so if we have something that's been minimized to the point of completely losing one of the everything depending on one particular variable, then if that variable changes, we can have glitches, but when we de-minimize, then we can eliminate that problem. So sometimes we want to minimize, sometimes we want to not quite minimize all the way. We have to look at how things are going to happen. So there we go. That is graphical minimization. So we've taken combinational logic and we've reduced it as much as we can for a systematic sum of products or products of sum form. And so what we'd like to be able to do next is implement combinational logic, and then after that we'll talk about sequential logic. So that's next, is implementing combinational logic.